All right, so in this last little section here, I'm just going to go through a theorem that they give at the end of this section about derivatives of uniformly continuous functions. And again, just like with the integral test, okay, this is another case where we're kind of looking ahead, okay, at something that we haven't technically defined yet, right? We haven't defined derivatives. And so the criterion of differentiability is actually sort of a sophisticated thing. I mean, well, I don't know. You'll see when we get there. But the true nature of differentiable functions, or like continuous functions that are not differentiable or whatever, is, as you might be starting to expect by this point, a little bit more hairy than you might have previously given it credit for from your calculus classes or whatever. Okay, so the main purpose of this, just like with the integral test, is that it's in situations where it's very clear cut what the derivative is, it kind of gives you like in situations where it's your basic calculus knowledge from before this class gives you a way to know what the derivative of a function is, then you have an easy way to assess whether that function is uniformly continuous, or at least sort of. I mean, it helps you analyze a function. So you can think of it as kind of a heuristic if you want, or whatever. It can help sort of flesh out your mental picture of uniformly continuous functions if you want. But yeah, so this is kind of like a sneak peek. Okay. And this is also a sneak peek at the mean value theorem. Okay, which says that if f is differentiable on a b, roughly speaking, let me, okay. I might make a tiny mistake when I'm stating it, but it doesn't really matter right now. Then there exists an x in a b such that, oh yeah, actually, I think you don't need differentiability, right? Because it doesn't make sense to. Okay, sorry. If f is continuous on a b and differentiable on the open interval ab, then there exists an x in the open interval such that f prime of x equals f of b minus f a over b minus a. So if you look at this, this is like sort of the, you can think of this as like the average rate of change of f over the interval ab if you want. So this is like the slope of the line that connects, the point at a to the point at b on the graph of f. It's also the average slope between those 2 points, or the average rate of change. And so basically it's just saying that somewhere in between a and b, f prime, the derivative, has to achieve the average value somewhere. Okay. And yeah, we'll prove that eventually, of course, once we define what derivatives are. But for now, you can just kind of take this for granted. And I guess I should just say that everything we're doing in this little discussion here, you probably shouldn't use anything from this discussion in a proof unless it is abundantly clear from context that it makes sense to do so. Okay, so yeah, it's just this is a lot of stuff that we haven't gotten to yet, but for the sake of just giving you a nice mental picture, I'd like to talk about it now, just like how the book does. I think it's a nice, it kind of ties together the idea of uniform continuity nicely with derivatives. So anyway, yeah. So just keep that in mind. So the theorem is this. So all right, it has kind of a complicated statement. So let f be continuous on an interval I, possibly unbounded in either direction, right? And let I circle the I minus, well, okay, the I with any endpoints removed. So quite literally, I mean, I circle is the interior of I in the topological sense. So is the interior of I, right? As we've seen. So if f is differentiable on I here, and f prime is bounded on I circle, then f is uniformly continuous on I. Okay? So yeah, like I was saying before, remember, like uniform continuity, one way of thinking about it, which I would discourage you from relying on too heavily, especially because like there are so many continuous functions that are not differentiable that, you know, it just really is bad to use derivatives as like a crutch for thinking about like how much a function can change, for example, because there are a lot of continuous functions that just don't have derivatives. So, but it's sort of like, this is saying that when the derivative does exist, you can kind of think about it as like the thing which modulates, you know, whether f is uniformly continuous, because it kind of controls how fast f changes. Of course, it's a very subtle thing. Okay, so this is not an exact, okay. And notice that this is not an if and only if statement. We're only proving one direction here, which is that if the derivative is bounded, then the function is uniformly continuous. Okay, and the only reason we have to do this like the interior of I thing is that like if f is only defined on I, and it's not defined for any points outside of I, then if I contains like an endpoint, like it has a closed endpoint, then the derivative of f just doesn't exist at that point, for our purposes, at least. Yeah, I mean, you could say there's like sort of a one-sided derivative, but that's kind of a weird like thing that we don't mess around with really. So yeah, we're going to just say that f is not, like, the derivative of f doesn't make sense at like an endpoint of the domain of f. So that's the reason that we had to do this thing. So anyway, the proof of this is pretty simple. It mainly hinges on the mean value theorem. So say m is an upper bound on the absolute value of f prime. So f prime of x, absolute value is less than or equal to m for all x in I. Right? So now, what do we want to show? We want to show f is uniformly continuous. Okay, so let's just use the definition. So let epsilon be greater than 0. Now we want to pick delta, right? Delta so that, you know, the difference between f of x and f of y, absolute value is less than epsilon whenever x and y are within delta of each other, right? So now it's like we want to use our knowledge of like the fastest that f can change is with a rate of like capital M, right? So take delta to be less than epsilon over capital M, okay? Right, because the idea is that it's like if x and y are spaced like delta apart, then I guess you can actually take delta equals. It doesn't really matter. If x and y are delta apart from each other, then like the most it can change between those 2 points is delta times the maximum rate of change. So that way, the most it could change is by epsilon, right? So then let x and y be in I with x minus y less than delta. Then the mean value theorem tells us, right? The problem is like, how do we actually capitalize on our knowledge of this like upper bound on f prime, right? Well, what we can do is we can find we can like represent the change in f between x and y as like, you know, the value of the derivative at a single point in between x and y times the width of the interval. So there exists, let's say, whatever. Oh, they use different notation, whatever. Okay, I'll call it x naught, whatever. Between x and y, such that, let's see, f of x, or sorry, f prime, right, f prime of x naught equals f of y minus f of x over y minus x, i.e., and then if you take absolute values on both sides and multiply by y minus x, we get absolute value of f prime of x naught. Well, yeah, let me write it this way. F of y minus f of x equals absolute value of f prime of x naught times y minus x, right? But then this here is less than or equal to m, and then this is less than delta, which is equal to, I guess, which is equal to epsilon over m. So overall, this is less than epsilon. Okay, so that shows that f is uniformly continuous if its derivative is bounded, at least in the situation where we're looking at an interval and the derivative is bounded on the interior of that interval. So yeah, okay, just as a very quick example, sure. So this is example 10. We can easily, right, and consider then, right, on a infinity, well, in fact, f prime of x, right, is negative 2 over x cubed, which is less than or equal to 2 over a cubed. So f is uniformly continuous on a infinity. Right. So this is a very easy way. I mean, obviously this is like assuming we know how to differentiate f, which is a whole other thing. But, you know, if you kind of take for granted that we know the derivative of f, then, you know, this theorem gives us a very easy way of assessing that f is actually uniformly continuous on any interval of this form. Okay. So anyway, that's all for this lecture. Thank you for watching, and I'll see you in the next one.